we'll be ready, I think. Yeah, we're live.
All right. Very good.
Yeah, we're live.
We're live? Okay, great. So, well, it's good to be back. Hi, everybody. Great to hear from you all, or see you all kind of in this digital new normal. So we've kind of come full circle now. I'm actually in my office in Trinity College Dublin after months and months of not being able to access it. So me and Mark discussed, and since it kind of coincides with the holiday time, we figured it was a good time to at least finish off this particular, let's say, series of the series. It's probably fitting that Mark gave the last talk and I hosted it. So just before we begin, since it's the last talk, I just wanted to make some thank yous and comments. So first of all, obviously, thank you very much to all of the speakers who participated here. I think that, you know, in the end, you know, we got really, really good and very high quality seminars, which now are available online thanks to the speakers allowing us to do so. And they're a very nice resource, I think, for our small community. I think the spread of topics was really nice. We managed to get a kind of nice representation from younger speakers, early career researchers to more established researchers on a range of different topics, sometimes a little bit outside the realm of quantum thermodynamics, but that's no harm either. In terms of thank yous, thanks very much also to people who didn't present, but who participated in the chat room, asked questions every week. I thought that was really good. We had some nice discussion, and everything was kept, I think, in an exemplary, polite style. And that's credit to the people who were involved and followed us week in, week out, sometimes twice a week. So we've had, I think, of the order of 35 seminars, which is, I think, a serious thing in itself. Before I thank the man of the hour, I'd also like to just say that often one of the postdocs here in Dublin, Francesca, she's probably tuning in now from Italy. She was often, actually she was the one which suggested this format and set up the way of streaming it, etc. And she was often there when we were having problems with this new concept in this pandemic of bitrate anxiety. Mark knows all about it now. It's something that you have when you try to do live streams and it doesn't often go well. I mean, obviously Mark took over for me at a very early stage because I had small children around the house driving me crazy streaming cartoons, and it wasn't sustainable. I guess the person that I'd like to thank most is Mark himself. I thought he did a tremendous job of keeping this thing going, contacting speakers, and also being a really good host in general. And I think just want to thank Mark from my own perspective. I think it was great. We'll see what happens with this situation, this plague that we're in at the moment. How long things. And so, I mean, in my country, things have quietened down, but this can change pretty rapidly. I hope things are going well for everybody else, and eventually, you know, things go back to normal. I just want to say before we start as well that although this was a great success, I still think that, you know, online seminars, they cannot replicate the sort of the one-to-one interactions and the one-to-many and many-to-many interactions that you get in real time. I think we can't possibly replace that, and I really hope to see you all at some conferences somewhere in the next period of time. At the same time, I also think that it's a particularly difficult period of time for certain members of the community that we mightn't be aware of. For example, early career researchers who face uncertainty due to the economic consequences of the pandemic. Researchers with caring responsibilities, whether that's young children or older parents or whatever. It's quite a difficult time, and I think more senior members of the community and people in stable positions should be mindful of that when making decisions in the future. So without further ado, I'd like to take you over to the man of the hour, Mark Mitchison, who I know very well, of course, and who's going to present work that we did recently in collaboration with a bunch of people, including those in Okinawa and UCD in Dublin. Thanks very much, Mark. Take it away.
Cheers, John. Thanks very much. I also just want to join John in saying thank you so much to everyone for kind of tuning in and participating in this thing. Thanks especially to Francesca for kind of working out how how to do all of this. And in particular, I also want to say thanks to John. I think this has been a brilliant idea of yours to set this up, and everyone in the community really appreciates you starting this whole thing. It's been great, and it's been really fun for me to kind of be part of organizing this and present, sort of hosting it. So yeah, it's a bit weird for me to be doing this from the other end, so to speak. So I hope that it works okay. Everyone already knows my computer has a habit of crashing, and it's like 36 degrees where I am in London. So let's just cross our fingers that it's not gonna do that today. But let's see. So yeah, I kind of replaced the title of this with a little bit of a tongue-in-cheek kind of title. So this is work about thermometry in cold gases. This kind of catastrophic quantum thermometer is what we've kind of jokingly been calling it amongst ourselves. I think it's a little bit more fun than this sort of dry title, but this is the title that you'll see on the archive, and it's going to be appearing in PRL at some point soon. We heard this week that it was accepted, so really chuffed about that. Yeah, so it's catastrophic not because it doesn't work. It's catastrophic because it's sort of a thermometry based on a very interesting many-body effect called the Anderson orthogonality catastrophe, and I'll be explaining what that is over the course of the talk. So before I get stuck in, I hope everything is kind of working. As I said, it's weird for me to be doing this from the other side where I can't actually check everything. So this was collaborative work done by a few of us in John's group. So of course me and John and Giacomo. This is kind of a very out-of-date picture of the group from when Steve Campbell was still kind of affiliated with us as an independent research scientist. Steve, of course, has now moved to University College Dublin to set up his own group. And the nice thing about this project is that it was sort of all conceived and done in faraway shores of Okinawa, which is a tropical island that's part of Japan. And we were there working with Thomas Bush and Mossy Fogarty in this kind of spaceship-like building as we were working out all of these ideas. So that was kind of a fun place to do science. So before I get on to like the actual scientific meat of the talk, I'll just give a very brief motivation for why we should be interested in thermometry and in cold atoms in general. So cold atoms are very interesting intrinsically, very interesting systems intrinsically, I think. And we've already heard from some people throughout the series. In particular, Jean-Philippe Rantou gave a really nice kind of introduction to those systems. I'm going to give a much more cartoony overview, but I just want to say that, I mean, aside from being the coldest objects in the known universe, they're very highly tunable. We can basically control almost everything about them, where they are, their geometry, and in particular, how the atoms interact with each other just by changing magnetic field. And that means that they have a lot of different interesting applications. So these are just a few snapshots from the literature. This is something that many of you may have already seen in the news. They recently made a BEC on the International Space Station. This is a picture of an astronaut actually holding the cold atom lab in her hands before it's going to be installed. Then this is something I read in Nature Physics like a couple of months ago. This I think is really amazing. This is where they basically used a Bose-Einstein condensate to image currents inside a high DC superconductor. And this is cool for me, I think, because basically, BECs have only been around for a couple of decades. I mean, the first creation of BEC was in '95, and this was a Nobel Prize winning achievement. And since then, we've learned so much about those systems that we now understand them well enough that we can use them to measure something else that we don't understand really at all, which is these high temperature superconductors. And then another application, which is of particular interest to people in our group, I mean, this is just one of many interesting applications, but this is particularly interesting for me. And this is where you can use these systems to really simulate something else that might be hard to kind of understand in another way. And in particular, there are now setups in cold atoms where one can really simulate kind of thermoelectric transport and these kind of small-scale thermodynamic processes, which can simulate electronic systems, but can also do things that wouldn't otherwise exist. You can simulate strongly interacting transport where the particles are actually attractively interacting. Of course, electrons always repel. So, I mean, we're yet to see really all the interesting physics that's going to come out of this. So with that kind of motivation, we'd like to be able to understand and probe these cold atom systems as well as we possibly can, so that we can use them for these interesting scientific applications. And our motivation for this work in particular is fermionic gases, which are a little bit less well explored than BECs, of course, have been around for a long time. And one of the kind of interesting recent developments in the study of cold Fermi gases is the realization of really homogeneous systems. So systems that are really in a box-like trap, and their density is uniform. And that makes them ideal for simulating all kinds of kind of canonical problems in condensed matter physics, which you always assume that the system is translation invariant, which is a good approximation for metals and many other materials, as long as we're kind of ignoring the lattice. So this is an interesting frontier in cold atom physics, but it's challenging because these systems are very hard to measure their temperature, right? And the reason is kind of obvious. It's because of their homogeneity. So basically the density, what you would normally do to measure temperature is look at the density of the cloud, and if it's in a harmonic trap, then essentially the hotter it is, the more spread out the system would be. But now, because the system is homogeneous, the density is the same everywhere, okay? So basically the size of the cloud is just the size of the trap, and you don't get any information on temperature. And that's for real space, but then you could also think about doing a measurement in momentum space, which you can do via time of flight. So you basically release the gas and you see how far it goes. But in fermionic systems, this is also challenging, basically because of this image. So all of these images are taken from an actual experiment where this was realized. And you can see here this kind of beautiful image of the shape of a Fermi distribution forming as you go to lower and lower temperatures. And at low temperatures, you can see that basically the vast majority of the atoms are in this region here, where their density, the momentum density, is completely independent of temperature. So hardly any of the atoms give you information on temperature. That makes thermometry really hard. So our proposal was to do something completely different, which is to basically dunk a probe inside the gas, and the probe will be an impurity atom of a different species, and use measurements on this probe to kind of infer the temperature. Okay, so that was a fairly long kind of motivation and introduction. So let me move on now to the actual the kind of content of the talk. So this is just a brief outline. First, I'm just going to introduce the basic idea of using a probe for thermometry, and in particular, our probe is going to work by quantum decoherence. All right. Then I'm going to move on to actually explain the experimental setup and this idea of the orthogonality catastrophe that you get in these Fermi gases. And then finally, we'll move on to this catastrophic thermometry, which is actually using this interesting dynamics to try and measure temperature. Okay, so let's start. So what is a dephasing probe? So let's think about a very general scenario where I have some two-level system that's going to be my probe, and that's described by some Hamiltonian HS. And this probe is going to be immersed in some environment at equilibrium at temperature T. And this environment is the system that I'd like to measure its temperature. Right? So there's some environment Hamiltonian HE and some interaction Hamiltonian HI. And I'm going to assume that essentially this Hamiltonian HS, so the system Hamiltonian, the probe Hamiltonian is a conserved quantity. So the energy of the probe doesn't change in time. Okay, and this then allows me to actually solve the dynamics exactly. Okay, so if I now imagine an experiment where I essentially prepare my environment in some thermal state at temperature T, and then I initialize my probe in a coherent state that's a superposition of the two probe energy eigenstates. So that's this state here on the Bloch sphere. Then if I evolve the system in time, I can write down an exact expression for the coherences of the probe. Okay, so I apologize. There's, like I said, it's 36 degrees outside, so I need the windows open, but there's the sounds of noisy Brixton coming in the window. So I hope that won't be too distracting. So yeah, the point is that we can solve for these coherences exactly, okay? And that's very useful from the point of view of a probe, because that means we understand very well what our probe is going to be doing, okay? And so in this solution, what I've written down is I've basically written down this overlap between the two probe states that we can measure in terms of two different Hamiltonians of the environment. So this Hamiltonian H0, which is basically the Hamiltonian the environment would feel if the probe were in state 0, and this Hamiltonian H1, which is the opposite. So it's the Hamiltonian that the environment evolves under if the probe were in state 1. Okay, and now the probe is in a superposition of these two states, so the environment evolves in the superposition of these two kind of scenarios. All right. So yeah, so the point of this slide is that everything about the environment's dynamical response is encoded in this decoherence function, which we can basically measure by just looking at the coherences of the probe. And this idea has been explored now in actually a huge number of works. So this idea of a dephasing probe, I apologize to the many of you whose works I will not have cited here. Lots of people in the audience have probably worked on similar ideas. These are just a smattering of ideas from the literature, specifically on cold atoms, where this has been used. And of course, what we're going to do is think about how we can measure this parameter temperature, this temperature T. Okay, so to do that, I need to just, before we get to results, I'll introduce some basic ideas about quantum parameter estimation, which is probably familiar to many of you, but for those of you that are not familiar with it, I have to just define what the basic quantities are, so you know what my plots are about. Okay, so we have this decoherence function, okay, which we can measure by looking at the qubit, and it depends on the temperature T of the gas. So now the question is, how precisely can we estimate this temperature just by making measurements on the qubit probe alone? Okay, and this, of course, this is a question whose answer is fully known, and it was answered basically by Brownstein and Caves in a very famous paper, which I highly recommend to everyone. We already heard Alessandro Silva talking about this, so I'll just kind of briefly recap the idea. But the point is that we make a bunch of measurements on our qubit probe. Okay, we make m measurements, which will give us a bunch of random outcomes, okay, which I denote by this vector here. And then I'm going to construct some estimator of the temperature, which is just some function of these measurement outcomes, okay? And this estimator is going to use the knowledge that I have about the dynamics of the system to infer the temperature from my measurement outcomes. And then the question is, what is the kind of expected error of this estimator, given that I made these m measurements? And there's a classic result from statistics that says this error is lower bounded by this quantity called the Fisher information, which has this kind of formal definition here, where these p of chi given t are just the probabilities of obtaining outcome chi, given that the system has temperature T. Okay, and so just to get a bit of intuition for what this quantity actually means, it's a bit of an unfamiliar expression. But if we think about the scenario where let's say our measurement outcomes are Gaussian distributed, okay? So everyone likes a Gaussian distribution. So our measurement outcomes are Gaussian distributed, and let's assume that the mean of this Gaussian is the thing that depends on temperature. So the mean x is the thing that I'm going to use to infer temperature. But the point is that I can only make a finite number of measurements, and due to this finite number of measurements, I'm going to get some kind of statistical error when I try and reconstruct the probability distribution. So the best that I can do is just make a bunch of measurements and make a histogram like this. And hopefully you can kind of see already intuitively that if the distribution of these outcomes is very broad, it's going to be difficult for me to distinguish between two sort of closely neighboring Gaussian distributions. So the Fisher information essentially exactly quantifies this fact. So it quantifies the fact that, first of all, the mean that I'm kind of trying to estimate has to depend on temperature. So in order to get temperature information, my mean has to be some function of temperature. And then I get this kind of statistical prefactor, which is proportional to 1 over the variance of this distribution, which basically says that I get more information if my distribution is sharply peaked. Okay, so if this delta is small. And we'll see this statistical prefactor appearing again in just a second. That's just why I wanted to kind of highlight this fact. Okay, so that's classical statistics. Now, in the quantum case, we basically have freedom to measure any observable of the qubit that we would like. And the famous result of Brownstein and Caves was to show that no matter what measurement we choose, there's always this upper bound on the Fisher information called the quantum Fisher information, which basically tells us what the best precision that we can hope for is. And it's the Fisher information of the optimal measurement. Okay, so this quantum Fisher information, the take-home message is the quantum Fisher information is how I'm going to quantify how good my thermometer can be. Okay, all right, so I'm slightly in danger of taking too long here, so let me kind of try and pass through this relatively quickly. But for the case of a pure dephasing evolution, we can actually get a very neat expression for the quantum Fisher information that has a fairly simple interpretation. So the point is that for this pure dephasing evolution, everything happens on this equatorial plane of the Bloch sphere. Okay, so my cubic coherence just rotates around and shrinks down to the origin as it dephases. And so there's really just two parameters of the qubit that are relevant. That's the norm of this Bloch vector, so that's related to the purity, and the phase. Okay, and if I look at the quantum Fisher information, I see that it essentially splits into two parts. The first one corresponding to a measurement where I try to estimate the norm. Okay, that's this F parallel. And then the second part corresponds to a measurement where I try and estimate the phase. Okay, and the optimal measurements for those two cases, for the norm, the optimal measurement is where I measure in this basis. Okay, and for the phase, as it's well known, the optimal measurement is where I measure in this kind of this mutually unbiased basis. Okay, but the interesting thing is that I can do better than measuring in either of these bases in general. If I measure at a particular angle that's kind of a mixture of these two, then I basically get the full kind of information that I would get from either measurement. And so this optimal measurement is this thing called the symmetric logarithmic derivative. And so this tells me what I have to measure in order to kind of minimize my uncertainty due to the finite number of measurements. And so I just want to kind of introduce this quantity Q, which sort of is related to the Fisher information, but it tells me about the relative error. Okay, the relative temperature error is the thing that I'm interested in. So this Q is my quantifier of precision. So if Q is big, basically I have a more precise thermometer. All right, so that's enough for quantum parameter estimation. So let's move on to the actual physics of the problem. So I'm going to explain what this orthogonality catastrophe is. And so it arises when we actually think about a particular experimental setup, which is the thing that sort of we're going to have in mind for the rest of the talk. And this is an experiment that's actually already, the setup's already been realized in the lab. So this is very much a realistic proposal. So the idea is that, as I said before, we're interested in these Fermi gases, okay? And I'm going to assume that I have a fermionic gas of just a single species of atom. So one atomic species, all in the same spin state. Now, we know in cold atom physics that at low temperatures, because we have short-range interactions, basically only S-wave scattering is relevant. And that means two things. First of all, it means that we can control the interactions very well because we can essentially tune the scattering length, which is the parameter that controls the interaction strength. We can tune this scattering length to essentially any value that we like by using a magnetic field. Okay, so that means we can engineer the interaction Hamiltonian so that the qubit probe, the impurity, which has two spin states, okay, but only one of those spin states is going to interact with the gas. The other spin state, which is this state 0, is just going to be completely non-interacting. Okay, and this can be done. And then the other thing that's nice is that essentially because of fermionic antisymmetry, when all the fermions are of the same species, they essentially don't interact with each other at all at low temperatures. Okay, so there's no S-wave scattering between identical fermions, and that means the gas essentially is just non-interacting. So it only interacts with the impurity. And that means then, following all the theory that I explained before, that we're going to get this kind of decoherence function where this H0 is just the Hamiltonian of a free Fermi gas. Okay, so these are just some fermionic creation and annihilation operators. This is some free energies. And then the H1, which I'm going to get when my impurity is kind of switched to the interacting state, is going to be the free Hamiltonian plus some scattering term, which describes how basically the gas atoms collide with the impurity and they ricochet off and go to some other momentum. Okay, and so what the actual experimental sequence would be is essentially the following. So you would prepare all of your impurity atoms in this non-interacting state 0, okay, and then allow essentially the system to reach thermal equilibrium at the temperature that you're trying to measure, okay. And so because the impurities are non-interacting, the gas just equilibrates to its normal thermal state, and the impurities are in a product state with the environment, okay. So that's one of our assumptions. Then you basically use a kind of Ramsey interferometry scheme. So you apply some kind of microwave pulse to prepare this probe coherence, which is then going to kind of decohere as it interacts with gas. And then finally, you apply another pi/2 pulse to read out the state of the impurities. And this is exactly what was done in this experiment. And you can see they were able to measure this this contrast. So this S of T is what I call this V of T. And so our idea was to try and really use this to see how well we can use this kind of setup to infer the temperature. All right. So let's try and understand this open systems problem in a little bit more detail. So, and this takes us to this very famous problem in condensed matter physics, okay, called the orthogonality catastrophe. So the question is, how does this free Fermi gas react when we switch on this impurity potential, right? And this basically, because it's a non-interacting gas, it's very nice because essentially it's sufficient for us to just solve the single particle scattering problem to understand the many-body physics, right? So I don't want to get too bogged down in all these details. This is just to kind of explain some basic aspects of scattering theory. You can find this in Landau and Lifshitz or any other basic textbook in quantum mechanics. But so the point is that we just look at the single particle Hamiltonian. So for the non-interacting case, that's literally just the kinetic energy. When we add the impurity, there's an additional potential term, okay, which is some short-range potential. And the point is that if we look far away from the impurity, then the solutions in this potential are just given by spherical waves with some phase shift called the scattering phase shift. And this scattering phase shift essentially incorporates all of the features of the interaction. So all of the properties and all of the effect of the impurity is incorporated in this phase shift. And this phase shift is related to the scattering length by this relation. So the scattering length essentially, if you like, the scattering length is a single parameter determining everything about the interaction between the impurity and the gas, okay? So that's going to be like our system bath coupling strength, okay? So then looking at this problem, Anderson came to a very famous conclusion, which is that essentially even an infinitesimally small impurity perturbation is going to render the ground states of the kind of interacting and non-interacting gas orthogonal. But even more interesting, this kind of overlap has this universal form. So n is the number of particles in the gas. It has this universal dependence on this parameter delta F, which is the scattering shift evaluated at the Fermi momentum, the Fermi wave vector. Okay, so this parameter is going to appear again in just a second. It's going to turn out that this kind of universal behavior, you can also see it in the non-equilibrium dynamics of this problem. Okay, so I hope everything is relatively clear so far. So this is how we actually model this kind of thing, and this problem is actually very interesting. It's clearly a kind of open systems problem, but it's a little bit different to the standard models that often we consider in that field, where we assume linear coupling to a bosonic environment and so on. But nevertheless, it's exactly solvable by this very kind of beautiful formula, which is called different things, functional determinant or Levitov formula. It has many different names. It's been derived in many different ways. But the point is that you can replace this decoherence function, which is this kind of many-body overlap between these kind of many-body unitary operators. You can replace this expectation value with a determinant in which only single particle operators appear. So all of these quantities are just in the single particle space, this H0 and H1. These are these single particle Hamiltonians that I just showed you. And this operator N basically encodes the Fermi-Dirac distribution of the gas's initial state. Okay, so this beta, of course, is the inverse temperature. Mu is a chemical potential, which fixes the density. And we're going to assume that the gas is homogeneous. As I said, this is the kind of most interesting problem for thermometry. We set some boundary conditions, not really important, and we use this kind of pseudo-potential approximation, which is just a standard way of describing S-wave scattering. I don't want to get bogged down in the details of this, but the point is that this parameter A is the scattering length. This essentially sets the coupling strength. Okay, so this is how we're going to control the coupling strength. And this coupling strength, as I already said, can actually be tuned experimentally by varying a magnetic field. Okay, and that's going to be very important for the results I'm going to show you. And just to let you know that in this kind of Fermi gas, there's a nice natural unit system that I'm going to express all the results in. So there's a natural kind of length scale, energy scale, time scale, and temperature scale, and they're all just fixed by the density. Okay, so these are just the natural units for the problem. Okay, so let's finally look at some results. So All right, so there's quite a lot of information here, so I'll try and take my time going through this, and try and keep it as clear as possible. So, so what am I plotting here? So the main panel, what I plotted is basically the time evolution of this decoherence function of the qubit for various different temperatures and coupling strengths. Okay, so these blue lines are for weak coupling, green are for strong coupling, red for sort of intermediate coupling. Okay. And then the dotted lines show zero temperature. The solid lines show a kind of small temperature, and then the dashed lines show relatively kind of high temperature. Okay, so when I say high temperature, this is actually the temperature that's sort of accessible in these experiments at the moment. So it's about 1/10 of the Fermi temperature, something like this. Okay, and you can see, of course, that the results are highly temperature dependent and coupling strength dependent, which is good, right? We want something to be temperature dependent so that we can extract information on temperature. But what we see is this kind of universal behavior visible in the decoherence function, at least at short times. So this is on a log-log plot, which means that the straight lines are basically showing you a kind of power law decay. So we basically get, for relatively short times, this universal power law decay in the time domain, where we see appearing again this universal exponent, where this delta F is the scattering phase at the Fermi surface. Okay, and that depends on the scattering length. All right, and this is very well known and has been discussed in all sorts of papers in the cold atoms literature, and before that, many decades before that, in the condensed matter literature, and it's the origin of this famous kind of Fermi edge singularity problem. And what that means is that basically, if you look at the absorption spectrum, so for thermodynamicists, this is more naturally interpreted in terms of a work distribution. So this A of omega, this is essentially the distribution of work done by switching on this impurity potential. And you can see that it has this singular behavior at a certain threshold frequency, and this is entirely due to this kind of power law behavior in the time domain, or if you like, the threshold behavior dictates this power law decay in the time domain. And so the reason why you get this power law decay is really to do with the structure of the Fermi sea. Okay, so if you think about what happens immediately after you switch on the impurity potential, so assuming that the coupling is relatively weak, what's going to happen is there's going to be atoms scattered in the gas. So they're going to be scattered to higher energy states potentially. But because of the Pauli exclusion principle, this scattering can only take place close to the Fermi surface. Okay, so it can't take place down here, because basically if I try and scatter an atom from here to here, then this state is already full. There's no way that I can scatter these atoms. So all of the scattering is localized close to the Fermi surface. And then as time goes on, this generates holes below the Fermi surface, and then there can be further scattering events which fill up these holes. This generates further holes, further down, and so on and so forth. So this is clearly a kind of slows down the decoherence process, and this is the origin of this kind of algebraic decay, as opposed to the usual, let's say, the usual expectation, which would be a kind of very fast exponential dephasing. Okay. But at some point, the temperature information that's encoded in this kind of finite width of the Fermi surface starts to kick in. And you can see that this kicks in at a time that essentially depends on the temperature, right? So at low temperature, it takes longer for this kind of to kick in. But at some point, we lose this power law decay, and we move over to this exponential decay that you can see here in these dashed lines here. And this sort of the exponential, the exponent of the exponential decay, if you like, is also dictated by this universal scattering phase, okay? But also depends on the temperature, crucially. All right, so I hope, okay, and just to go back to these kind of absorption spectra, just to be clear. So I mean, basically this structure, this kind of singularity that you can see, this is really this is somehow a manifestation of the orthogonality catastrophe. It's the fact that essentially as time goes on, eventually there's going to be particle hole excitations created at all possible energies, okay? And this is going to completely destroy the Fermi sea, essentially, so that you get this kind of diverging contributions as a consequence of this orthogonality catastrophe, all right? Okay, so I'm going to stop talking about this now and move on to the thermometry. Of course, if people have further questions, then perhaps they can ask them at the end, and I'll see if I can answer them. This was completely new to me when I first started this project. So anyway, let's move on. So now the idea is to try and use this kind of features to infer some information about the temperature. So we're going to get our catastrophic thermometer. And so we can use these results and we can just numerically kind of calculate the quantum Fisher information that you would expect for a probe as a function of the time at which you measure and the temperature of the underlying gas. And you can see, well, of course, the results depend on both temperature and they also depend on the time at which you measure. So this Q, just to remind you, this is this quantum signal to noise ratio quantity, which I defined before. So large Q basically means a small relative error, or a small relative error can, in principle, be achieved. Okay. And so what you can see here, first of all, you see that basically as you move to lower temperatures, you have to wait longer to get good measurement precision. And this makes sense. I mean, this is exactly what I showed you on the previous slide, the fact that there's some sort of time scale which basically goes as 1 over the temperature, after which the thermal effects kick in. So before that, basically, the system just looks like it's at 0 temperature. And then the other thing just to highlight is, I mean, just if you actually plug in the numbers and you ask how good is this thermometer, it's actually pretty good. I mean, it's at least, you know, within the approximations and assumptions that we're making. Of course, we're neglecting lots of potential sources of noise, but you could achieve, you know, you could get about 10% relative error with about 500 measurements at an experimentally relevant temperature of 1/10 of the Fermi temperature. And although 500 measurements might seem like a lot, actually you could quite easily have 1,000 impurities embedded in just a single realization of the gas. Many thousands, indeed, in these experiments that have already been done. All right, so the thermometer works. That's good. So then we can ask, like, how can we sort of optimize this thing, right? So we know that we can play around with the coupling strength. How can we optimize this coupling strength to get the best possible precision? And the answer that we found is basically that weak coupling is the best. And that's not necessarily immediately obvious. I think it was a bit surprising for us for a long time trying to understand this. Maybe for those of you who are a bit more familiar with the kind of thermometry field, it's a bit more intuitive. So I know people like Luis Correa, whose work actually I think I meant to add a citation to the review in this, and I'm afraid I didn't. So if you're watching, Luis, sorry, but you should check out his review. It has all sorts of information about this kind of problem. But so for us anyway, this was kind of surprising. But we can understand why. But before I get onto that, I'll sort of tell you what we found. So basically, the best precision occurs at weak coupling. So when the scattering length is small, but you have to wait for a long time. So you have to pay in time. Okay, you get better precision, but you have to pay in the time that you wait before you measure. And you can see that in this plot here. So this blue line is, again, so similar to the plots I showed you before. Blue line is weak coupling, red line intermediate, green line the strongest coupling, and this QSNR is the highest for this blue line. Okay, and a simple way of understanding why this is the case, you can see that just by looking at the time domain evolution. So these blobs that are highlighted here in this plot correspond to the ones highlighted in this plot. And what I've done here in this plot is basically show how the block vector evolves in the equatorial plane as it kind of rotates around and decoheres to 0, okay, over time. And so you can see that essentially for the weak coupling case, this decoherence occurs more slowly. So at times where the temperature can actually sort of some information on temperature actually starts to emerge, the purity of this qubit state is higher, okay, or the norm of the block vector is larger, and that's very important because it relates back to the statistical prefactor for the Fisher information that I mentioned before. So the fact that essentially you want your distribution to be more sharply peaked, to be somehow more pure in some sense, in order to get a sharper estimate of your parameter. And in particular, if we go back to this expression for the quantum Fisher information, which I hope you can see, you can see that in these prefactors here, that basically for the bigger that the norm of V, the block vector is, the bigger that both of these terms end up being, right? So then, I mean, if we look at how this behaves as a function of temperature, essentially this holds for all the temperatures that we looked at. So this kind of qualitative picture applies at all temperatures. And then we can ask, like, what are the limits of this thing? So how good can we make this precision? And this was another kind of cute result. It turns out that essentially there's no limit to how big one can make this quantum signal to noise ratio in principle. So as you reduce the coupling strength to smaller and smaller values, this thing actually diverges. So the maximum value attainable of the QSNR actually diverges. Okay, and we can show this analytically. I'll go through this a little bit later on. But the point is, again, this is not a free lunch, because as you reduce the coupling strength, you have to wait for a longer and longer time. So in practice, one can never actually achieve this infinite precision, because you'd have to wait for an infinitely long time. And in fact, the time that you have to wait starts to diverge faster than the precision gains at some point. Okay, so all right, so let me move on and try and just talk a little bit more about why we think this weak coupling helps. So first, I'll just present a very kind of intuitive picture, which actually is most of the explanation, I think, in the end. So why does weak coupling help? If we go back to this picture of how the sort of excitations are created in the gas, I'll just remind you that for weak coupling, basically what happens is, at least initially, most of the excitations are created close to the Fermi surface, okay? Because there's just not enough energy to promote them to very high energy states, okay? But for very strong coupling, essentially from the very beginning, we start to create excitations with very large sort of single particle excitations, particle hole excitations with very large energies all over the Fermi sea. So not just localized close to the Fermi surface. And then you can kind of intuitively see then that these kind of low frequency excitations can sort of feel out the shape of the Fermi surface more easily than these high frequency excitations that just obliterate the whole thing immediately. Okay, and the shape of the Fermi surface, of course, is what encodes the temperature information. Okay, so that's an intuitive picture, and then to try and get a bit more quantitative, we can actually look at the numbers we get out of the Fisher information, and we saw that actually it's the phase of the decoherence function, which so far I barely really talked about. It's the kind of the complex phase that contains the most temperature information at weak coupling. Okay. And this we can also understand. Okay, so this plot, I'm just showing you again the behavior of the norm of the decoherence function, which of course is decaying more slowly for weak coupling. Okay, and now I'm also showing you the phase that we calculated. Okay, so the phase evolution itself is kind of boring. That's why I haven't really plotted it up until now, because it's basically just a linear function of time, where this W essentially tells you what the rate of phase accumulation is. Okay, and of course for stronger coupling, the rate of phase accumulation is faster. But if we look at how this rate depends on temperature, then we see at weak coupling this temperature dependence is strongest. Okay, and this again reflects this fact that I already told you about how for very strong coupling, you kind of just obliterate the whole Fermi sea. The excitations don't really see the Fermi surface, and so all of the properties become more or less independent of temperature. But for weak coupling, this phase accumulation rate really does depend on temperature. And so then you can see what you have to do to get a very precise estimate of temperature. You basically just have to wait a very long time so that this phase can accumulate to a very large number, and that will allow you to very precisely distinguish between small changes in temperature. And that's exactly what we're finding with this diverging precision. It's just saying that the very, very slow decoherence allows a very long time for the phase to accumulate, and thus for you to kind of extract information on temperature by a phase measurement. All right, so I'm nearly at the end. But I mean, one thing that was kind of nice is that we were able to actually sort of show this by some analytical calculations that I'll just briefly go through. I don't want to get too bogged down in detail, but for those of you interested in open systems, this is kind of a cute calculation. So the point is that we can actually show that this fermionic reservoir, if you like, actually behaves like a bosonic bath for low frequencies. Okay, and so to do this, we use this kind of cumulant expansion technique of so we go back to this kind of many body representation of the decoherence function, and we just use good old fashioned second order perturbation theory essentially. Okay. And what we find is a decoherence function of this form, where we get this kind of linear phase evolution that just depends essentially on the average value of the perturbation, this collisional interaction between the impurity and the gas, and then this gamma, which basically dictates the rate of decoherence. Okay, but it's not just a linear function of time; it's actually a highly non-trivial function of time. And so to calculate what this is, you have to look a little bit at the spectral density. And so the spectral density for this fermionic problem can be defined like this. So this is probably quite unfamiliar to many people that are used to working with bosonic reservoirs, but it kind of makes sense. Okay, so basically what you have is the coupling strength squared as usual, okay, weighted by the density of states at the corresponding frequency, but then this is also weighted by these kind of fermionic occupation factors that basically just tell you that you can only create a particle hole excitation if there's a sort of filled state at this energy and an empty state at this energy, and that's what allows you to kind of promote this particle from the filled state to the empty state. Okay, so if we look at this thing at very low frequencies, then we find this expression, which is exactly the expression for the spectral density of a bosonic bath with an ohmic spectral density function. And we get this appearance of this bosonic occupation factor. So that tells you that basically particle hole excitations near the Fermi surface, they actually behave like basically like bosons. So roughly speaking, you can kind of think about it as a pair of fermionic excitations creating a boson, and then you get this coupling strength alpha, which depends on the scattering length. Okay, but crucially, it depends on the scattering length squared. Okay, and then finally we get this expression, which you can show by some contour integrals or whatever. But the point is that this works for low coupling strength. Okay, for low enough temperatures and for kind of weak coupling, you can check against the exact numerics that this sort of starts to work pretty well for coupling strengths on the order of 0.1 or so. Okay, so that's very weak coupling. Fine. Okay, so using this, we can actually derive some analytical results. So this plot you've already seen. It's just showing you what the temperature dependence of the phase accumulation rate is. And this is just showing you essentially this dotted line is the analytical result valid for very weak coupling. So you can see that as you move to weaker and weaker coupling, the results the exact results kind of converge to this analytical result. And okay, I think maybe I shouldn't go into too much detail, but I'll just reiterate the basic point, which is that essentially we have these two competing effects. We have this kind of decoherence, which causes a loss of purity and tends to make it harder for us to kind of distinguish this kind of temperature parameter. And then we also have this phase evolution, okay, which kind of encodes the temperature. And the point is that for weak coupling, as you make the coupling weaker and weaker, the rate of decoherence gets slower and slower, but it gets much slower compared to how the rate of phase accumulation slows down. So both slow down, but the phase becomes the dominant effect compared to the decoherence. And you can use that to basically show that, you get these analytical results for the precision, which essentially explain these kind of asymptotic results. Okay, so I think I should probably move on because we're going to run out of, I don't want to take more of your time. So before I kind of summarize, I just want to say, it's been a privilege to be able to present as part of this series, and I'm kind of representing the whole QSIS group in being able to do this. So I'm very happy to be able to do this, but I kind of want to highlight some of the other amazing work that's been going on in our group. So this is just like a kind of cloud of paper titles that I took from. These are all just things that have been published this year or will be published soon this year, just to kind of give you an idea of the different range of topics that have been covered. And I just want to say that I think everyone in the group has done kind of exceptionally well in very difficult circumstances. And the kind of range of topics, I strongly recommend you go and read all of our papers. It covers pretty much all of the topics that we've heard discussed throughout this series. And yeah, I look forward to kind of talking with many of you and collaborating with all of you on any and all of these topics in the future. So let me summarize the talk. So basically, the idea was that we can use this kind of quantum decoherence of an impurity to probe the temperature of a cold Fermi gas. And it's kind of nice because other thermometry techniques actually struggle due to the Pauli exclusion principle, whereas this technique actually kind of exploits the Pauli exclusion principle because it gives rise to this very slow algebraic decoherence that then allows us to do this kind of phase estimation thermometry. Okay, and so it would be interesting to look at this in other geometries. I just told you about the kind of 3D spherically homogeneous case. We did look at the one-dimensional case, harmonically trapped case. All of these cases seem to work very well. In general, one has to basically solve just a single particle problem to do this in an experiment, so it's kind of an efficient estimation procedure. In practice, you only have to solve a kind of computationally efficient parameter estimation problem. And I think, metrology in general gives kind of a nice perspective on many body systems and on open quantum system dynamics. So it's been fun for me to learn a bit about this. And of course, there are many other works in the literature which which I'd kind of recommend you check out on thermometry by other people who know much more about it than I do. And of course, we're interested in looking at generalizations of this. And if anyone has any kind of ideas, of course, we'd be happy to hear from you. With that, I thank you for your attention.
Very nice, Mark. Thanks very much.
Thanks.
We have a number of questions from the YouTube. Let me just see if I can start with the first one that was asked. Okay, so the first one here was by Stefan, who asks, in the plot of the Fisher information term Q versus T and small t, so big T and small t, where would the curve of T equal to H bar times beta lie? Because usually H bar times beta would be something like the thermal correlation time of an environment.
Right. Yeah, I mean that's a very important time scale here. Maybe I should have emphasized that a bit more. But essentially, it's not exactly correct, but roughly speaking, the area where these peaks sort of occur. I mean, it moves. Well, okay, no, that's actually sorry. That's a little bit. I was about to say something nonsense. So on this curve, where would the H bar of a KBT lie? Well, this is actually this is all at one fixed temperature. This curve is a function of time, so you can see that the peak. The peak doesn't actually occur. It shifts as a function of the coupling strength. I think for this case. So what exactly is it? This is a good question. I actually don't know. I'm guessing. I mean, it's certainly going to be somewhere around here, I guess. Right.
So Stefan follows up with the following question, which maybe makes sense. He says, do you get your maximum Q values always below this correlation time, suggesting some sort of non-Markovian effect?
Yeah, no. I mean, in general, no. If you look at this plot, because basically I suppose the thermal correlation time is somehow it's somewhere around here, I guess, right? Yeah. I mean, and this guy reaches a maximum much later. So this plot is already in the regime where kind of most of the information, I guess, is being imprinted on the phase. In the regime where most of the information is imprinted on the norm, I guess the peak, generally speaking, occurs around about exactly at the thermal correlation time, because basically that's the point where the norm. So that's where the norm starts changing, right? So the thermal correlation time on this plot, it really is given more or less by the points at which the sort of the dashed line or the solid line starts to depart from the dotted line, right? So this is high temperature, it occurs sooner. This is a lower temperature, it occurs later, and so on. Mm-hmm. So I mean, I don't know. I hope this answered the question, but we didn't really look at the problem of Markovianity here at all. I mean, I think that's what he's angling at. But that's kind of an interesting question for future work, for sure.
So thanks, Stefan. Just try and get through some more of them. So there's a question here by Ivan Henau. Have you considered what happens if your probe cannot be initialized in exactly a pure state?
Yeah, I mean, that's a good question. I mean, no, is the answer. We did not consider that. But
there would be no problem
course,
looking at that if we wanted to, let's say. I mean, so
exactly, one could look at that. I think for most cases, for the scenario we have in mind, it's not actually that relevant because the probe would be really in a pure state to a very good approximation in these experiments. But there are scenarios where maybe it wouldn't be. For example, in a scenario where perhaps you have some system environment correlations. I mean, generally, what I would expect is that would degrade the thermometry.
It can only make it
open system dynamics.
Yeah, I think it can only make it worse, right?
Yeah, because of this thing about, I mean, you want your purity to be high. Yeah. Essentially, you need high purity to get good estimate.
Right, so let's move on. From Junji Liu, Mark, since there's an interaction between the thermometer and the Fermi gas, can the measurement be quantum non-demolition?
Yeah, so we discussed this a fair bit amongst ourselves as well. I mean, I don't think it's correct to call it a non-demolition measurement. I think one could call it a minimally destructive measurement, in the sense that some conventional thermometry typically works by literally obliterating the system. I mean, by switching off the trap that holds all the atoms together and just watching it explode. Okay, so that's demolition thermometry for sure. Okay, so this is non-demolition in the sense that it doesn't completely destroy the system. There is still a Fermi gas at the end of the measurement, but it's very much not in a thermal state anymore. Yeah. After the measurement, I would say.
Fair enough.
And that's the essence of the orthogonality catastrophe, right? I mean, it's really
I think that this actually answers the next question, actually, which is by Miskin Khan, and they say, does thermometry require thermal equilibrium between the system and the probe? And can the out of equilibrium situation also provide an optimal thermometry conditions? And I guess you just answered the question in the sense that the only thermal equilibrium that we ever have here is at time zero, right? So.
Right, yeah. And I mean, I guess I would also just add, I mean, everything about this scheme I should have mentioned is completely non-equilibrium in the sense that the probe cannot equilibrate. I mean, because of the structure of the interaction, it just cannot equilibrate. There is no equilibration here. So all of this stuff is completely non-equilibrium, which is nice because then you don't have to wait for equilibration.
Yeah. Okay, so moving on, another question by Ivan. Since you get optimal results at long times, is it possible to compare results with the case of a probe that fully thermalizes with the gas?
Right, which touches on essentially what I just said. Yeah, exactly. So I mean, I guess one could. We didn't do this. But that's an interesting point. Yeah, I mean, you could certainly compare what kind of Fisher information one could expect in those different cases. The problem of an as far as I understand, the problem of a kind of equilibrating probe was essentially posed and solved in full entirety by Luis Correa and many others in a PRL from quite a few years ago, right, where they basically showed exactly how to engineer the level structure of the system to get optimal thermometry. So in that sense, the results are there, and we could just check. And I suppose one can always find some kind of some probe with some appropriate level structure that could beat this system. The question is how easy it is to actually engineer the energy gaps, right? Because for equilibration thermometry to work, especially with a qubit, you need the energy gap to be on the order of the temperature. Yeah, and that can be very difficult at low temperatures, and we don't have any such restriction here. The energy gap of the qubit is irrelevant for this.
Yeah, and I mean, just to emphasize again, I mean, the reason why we chose the setup that we did choose was because it had been performed in an experiment, not for thermometry, but to study this decoherence function. I mean, there's an experiment that Mark showed from 2016 or whatever, which precisely extracts V of t, or mod V of t. So that was sort of what the motivating factor was. Just moving on, there's a question from Irene, who asks again about interactions. So what are the role of if you had interactions like a Fermi liquid, how would the results change?
Yeah, I mean, that's a very good question, of course. So I guess if it was really a Fermi liquid, in the sense of Fermi liquid theory, then essentially I would expect for weak coupling and low temperatures everything that I've said to be the same, right? Because we know that essentially for kind of relatively weak perturbations close to the Fermi surface and at low temperatures, Fermi liquid theory tells us that essentially the quasi-particles in an interacting Fermi gas behave as if they were non-interacting. So, but as soon as you go to the strongly interacting, sort of strong collisional coupling or high temperatures, then I mean, your guess is as good as mine, Irene. I have no idea, and I'd love to be able to find out, but of course, then the problem becomes an absolute nightmare to solve.
Yeah, I mean, if you were in 1D, I guess, and you had strong interactions, you could probably appeal to like a Luttinger liquid or something and map the free bosons completely. But outside of one dimension, I think is very difficult with strong interactions to answer the question. I mean, So that'd be my take on it anyway. But so Philippe Barra, hi Philippe, long time no see. He says, hi Mark, does the fermionic bosonic correspondence depend on the choice of V of R?
Yeah, that's a good question. I honestly, I don't know because I only ever did it for this potential, but I would be almost sure that it does not depend on the choice of V of R as long as it's short ranged. And I mean, the reason for that is actually closely related to what John just was talking about. So this fact, which is well known in the condensed matter literature back to the 60s. I mean, all of this that I've showed you has probably been calculated before many years ago, and it's to do with the fact that the problem here is essentially one dimensional because of this. Okay, so I've kind of okay. So let me finish what I was saying, but so as long as the potential is spherically symmetric and short range, then I think it won't matter. And the reason why is that with spherical symmetry, essentially because you only have spherical waves being relevant, you only have S-wave scattering, the problem becomes effectively one-dimensional. And as John just said, it's well known that in one dimension, fermions, statistics is ambiguous, and fermions can always be kind of mapped onto some affected bosonic problem at low energy. So I would expect that this some bosonization-like trick could always be used to do a similar thing to what I've shown you here, but that would assume sufficiently low temperatures and short range potential so that sort of S-wave scattering is the dominant effect.
Yeah, I think that's fair. So there's a question then from Devira. Hi Devira, how's it going? She asks, if the decoherence function depends on the fermionic bath spectral density, how do you extract the temperature if you do not know the dispersion relation of the fermionic bath?
Yeah, I mean, so you're hitting on a very key point there, of course, Vera, which is that you do have to know quite a lot about your system in order for this to work. So that's, one of the kind of key points about parameter estimation. It only makes sense if you actually have a very good model for how your sort of measurement results depend on the underlying parameter, in this case, the temperature. So we are assuming here that you have quite a good understanding of the gas. But all you really have to know, I would say, is essentially assuming that it's really a non-interacting gas, which is true to a very good approximation in these kind of systems. All you have to know is the shape of the potential, okay? Because then you can basically solve the Schrodinger equation for a single particle, and you can find the dispersion relation numerically, and you can do this quite efficiently. So yeah, you have to know the dispersion relation, but it's relatively easy to calculate. You don't have to solve a many-body problem.
Right. Okay, so thanks a lot. The next question is by Ram. Hi Ram, long time no see too. Unfortunately, I missed your talk because I was on holidays, but I looked at it in post-process. He says, hi Mark, I imagine that if the probe is not ideal and has some intrinsic dephasing time, it will degrade the resolution. Is there a simpler relation between the probe decoherence and the resolution? I guess he's asking about additional source of decoherence,
Right.
On top of the natural thing that comes from being in a contact. But I mean, in cold atoms, I guess these sources are still, timescales are well separated, I guess, right?
Yeah, so we'd have to...
We'd have to work it out.
To be fair, we didn't think about that much. We have to work it out. I mean, I guess the dominant source of dephasing would be magnetic field fluctuations. I mean, as far as I understand, experimentalists are unbelievably good at controlling magnetic field fluctuations in these systems, because that's how they're able to explore this interesting spin physics.
Yeah, I mean, in also this species selective dipole.
But yeah, I mean, basically, I think Sorry, say that again.
So I was also thinking that you might think that there might be noise in this species selective dipole potential that holds the impurities, which would, but I don't know. I mean, I don't know what that's like. I know.
But no, I mean, that's a good point. It depends, I guess. I mean, if the two different spin states interact differently with the polarization of the potential, then you would also get dephasing there. Yeah.
But we didn't.
I mean,
we didn't kind of think about
a
it.
bit too much into technical detail.
Yeah.
Like, I mean, the basic point, I guess, to answer your question, Ram, is that it would definitely enter. I think it would degrade the resolution in the sense of it would enter into these statistical prefactors, right? So basically, it would reduce the purity of the state. I mean, if it was really just dephasing in the sense of it just contracts the block vector to the center, then it would just reduce the kind of the phase contrast. So it would reduce the purity and therefore would reduce the precision, and it would enter completely into these prefactors, I think.
Yeah, I see.
But it would affect the thing in principle, if it was comparable to the timescales that we're talking about.
I see one last question here as well from Angel Rivas, so he says, since the symmetric logarithmic measurement depends on the unknown value t to be estimated, do you have in mind some kind of adaptive measurement scheme to implement this kind of thermometry?
Right, yeah, thanks for bringing that up. That's a very good point. One that I kind of completely glossed over, and one that I also got very confused about when I was first learning about this whole quantum metrology thing. So indeed, I mean, it looks very weird, right? I'm telling you that you have to measure this observable to get the temperature, but the observable, you don't know what observable to measure until you already know what the temperature is, right? So indeed, yeah, that's what I'm thinking of, is some situation where, let's say you have some very rough idea initially of what the temperature is, okay? And then you set your measuring basis to something that would be reasonably good. You do a bunch of measurements, you extract some estimate for the temperature, which then improves your knowledge about what the temperature is. This allows you to do another measurement, sort of inputting that information from the previous one. You choose a slightly more optimal measurement basis and so on. And as Angel suggested, yeah, I mean, if you do this adaptively, then eventually you can kind of hone in and in principle, achieve the best possible precision that statistics theory allows you to achieve. But yeah, it would require some kind of adaptation.
Yeah. So I think, yeah, we kind of debated this sort of the reality of doing a thermometry with this technique in cold gases for a long time in Okinawa. And I mean, until someone actually goes about and tries it in an experiment, I think it'll be very hard to say whether there's any advantage actually over the kind of very crude way of just doing time of flight, which is a very crude way of measuring the temperatures, but it's the temperature measurement that every experimentalist in cold atoms uses. So I guess we don't really know whether it offers advantages doing it this way, but let's see. We hope that it maybe gives a different perspective at least anyway. I mean, I think you agree with that, Mark, right?
Indeed. Yeah, absolutely. Yeah, and I mean, if there are any experimentalists watching, please feel free to implement the proposal,
or tell us that it's nonsense. It's okay.
Yeah.
Actually, there's another question by Karen. How's it going, Karen? I haven't seen you in a long time either. Hope you're well. So he said, would the common evolution with the gas correlate two impurities? And if yes, would measuring two impurities jointly improve the thermometry? I think that's a very good question. But Mark, you
thanks. Yeah. I love that question. Yeah, well, as John knows, I love this kind of problem. And this is something we haven't looked at this. It's a very good question, and I expect you're right that first of all, indeed, in principle, two impurities would become correlated. I think that's just a beautifully interesting problem in its own right, and I plan, we're planning on looking at this in the future. And then with regards to thermometry, I would expect. So there's already been results in the literature for kind of bosonic case suggesting that you can get some enhancements from these kind of correlations, but you have to do some sort of global measurement. I actually think this is kind of interesting because if you're not able to access global measurements, probably the correlations actually make things worse, right? Because you no longer have basically independent measurements. So actually, in some sense, the kind of the M, you effectively would reduce this M that appears in the kind of Cramer-Rao bound, because you no longer really have M independent measurements because some of your impurities are correlated with each other. But of course, if you can exploit really global measurements, you can do some kind of measurement in entangled bases and so on, then probably you can get some advantage and maybe even some kind of quantum enhanced metrology scaling. But yeah, we haven't looked at that.
Okay, so thanks, Karen. And I think maybe that's probably the lot. Let's just kind of wrap it up here. I think it's a good point to bow out. I guess we'll all sort of miss the seminar series, but I think it's important that we build up some absence, because depending on what happens in the coming months, I promise that we'll be back at some point to keep the show on the road. Like, the show must go on, as the man says. But I think probably, you know, it's better that we kind of cut it out here. And in the meantime, maybe just for all of the community and people who kind of tuned in, perhaps it's just a good idea if you know, good speakers that haven't given a talk, and with maybe a long winter in mind, depending on what happens, we'd be damn glad of hearing from people, because it's unlikely, I guess, that there'll be any foreign travel or much foreign travel in 2020 in any case. And I guess we're all missing, meeting and interacting with the community. I think, personally speaking, remote working has its place, and it doesn't replace, interactions in live. It's terribly bad in my mind for the creative endeavor, the creative part of our job. So I don't see it as a long-term solution. But in the meantime, we can probably think maybe in the winter of doing a second round of the series. So with that, thanks very much again, Mark, for everything. Thanks very much for the talk today. Thanks very much to the audience, and we see you when we see you. Take it easy. Bye-bye.
Thanks, everyone. Bye.